All right, so what we have here is a problem directly from your homework. This is obviously number 2. I'm just going to kind of run through quickly how to work this particular problem. That way you guys have an example to go on for the future. So we have a 55 kilogram uniform sign hangs from the 2 ropes as shown. Uniform is kind of a big deal. That means the center of mass is at the middle of the sign. So whenever we look at the torque exerted by the weight of the sign, that will always come from the center of the sign. I ask, what is the tension in the left and right ropes holding the sign up? So first thing, even when we're working torque problems, I still like to look at the net force on everything. So we know this thing is in not only equilibrium, but it's in static equilibrium because it's completely stationary. It's not moving, it's not rotating, nothing. So I would say the net force is equal to 0. My 3 forces acting on this would be the force of gravity, negative mg, coming from the sign itself. The tension in the leftmost cable right here, we call that TL. And then the tension in the rightmost cable, we call that TR. TL and TR are both forces. The forces going upward, tension in the left cable, tension in the right. So what we have to do here is look at problems in a way we have yet to do so. We have to look at the torque and the net torque on this particular sign on this particular example. So what we are going to do is look at first the torque acting on the leftmost cable. So as we do that, we look at how would the other forces act on the leftmost cable. So as I look at this first, I would have 2 forces. I would have a torque coming from the sign itself. So the sign is here trying to make it rotate downward. So if that sign is here trying to make it rotate downward, well, downward from the left cable would be considered clockwise. So we're going to consider that positive here. Now, on some problems, on some answer keys, they switch positive and negative with clockwise and counterclockwise. It really doesn't matter as long as you keep it the same. So when I solve problems, I like to make clockwise positive, counterclockwise negative. So we first look at the torque acting on, once again, the leftmost cable. Well, the center of mass, this is a 1 meter sign, and the center of mass is going to be at a distance of 0.5 meters from each edge. So we have 0.25 meters here. That means the torque from the sign on the left cable is going to be another 0.25 meters away from that. So when we find the torque, which we know is just radius times the perpendicular force, and that perpendicular force is just going to be mg in this particular case, we would do 0.25, the distance from the left cable, times m of the sign, which is 55 kilograms, times g. Then we have the other force that will act as a torque on the leftmost cable. That's 0.75 meters away. And that one would be acting technically upward. So if that was causing it to rotate, it would rotate counterclockwise. So we're going to treat that one as a negative. So that'd be negative 0.75 times TR. We don't know the tension in the rightmost cable. That's actually one of the things we're trying to find. What's the tension in those 2 ropes, in those 2 cables? So we go through. We still know it's in equilibrium, so that'd be 0 equals. We know this term right here, mg sine, is 55 times 9.8. I multiplied that by 0.25, and I got a positive 134.75 minus 0.75 TR. I get the tension in the rightmost cable is equal to 179.67 newtons. So I found the tension in the rightmost cable by looking at what's going on the left cable. So we're going to do the exact same thing here, but now we're looking at things in terms of our right cable. So we know this net torque here is still equal to 0. But now we're going to look at everything from this perspective right here, from this point. So mg from the sign, that torque there, if we look at that, we need to say, what's that going to make the rightmost cable do? Well, if this torque were allowed to rotate from the rightmost cable, well, that would be going this direction. that would be counterclockwise in this particular case. So that's going to be negative. And then the force is going to be, of course, the mass times g of the sign, the force of gravity of the sign. And then we need to look at the torque coming from the leftmost cable. That's 0.75 meters away. And that would be acting clockwise, because if you look at how that's being pulled, that would pull it in the clockwise direction coming from there. So we're going to treat that as positive. So I do the same thing I did previously. 0 equals negative 269.5, those two numbers multiplied, plus 0.75 TL, and I get the leftmost cable is equal to 359.33 newtons. I'll put a box around that to show that, hey, that's a final answer. Now, great way to check to make sure that we did these problems correct. We found two forces, tension in the left, tension in the right. Well, we just said net force should be equal to 0. So if I take a look here and I take a look at force of gravity on this, which would be negative mg. Let's get this calculator so we can actually still see my answers. I would have negative mg, negative 9.8 times my sign's mass, 55. Well, that plus the tension in the rightmost cable, 179.67, plus the tension in the leftmost cable, plus 359.33. You guys tell me. We should see the sum of those three numbers equal to 0, because the net force is equal to 0. Bam, we get 0. Everything's happy, well, and good. So there is a simple intro torque problem. You guys will, of course, have more difficult ones, but we'll work through them together, or, well, you guys on your own until you have me. So anyway, there you go. Thanks. Rewatch it if you need to, and do your homework.